Hello everyone, I'm Gia Lekabankali, and together with Katrina Joy Tanio, we're here to discuss about rational functions. Rational function is any function which can be written as the ratio of two polynomial functions, where the polynomial in the denominator is not equal to 0. Before we proceed to the discussion, let's all take note of these key points. Domain, the set of all input values x over which a function is defined. Singularities, x values at which rational function is not defined, for which the denominator q of x is 0. Vertical asymptote, a vertical straight line which a curve approaches arbitrarily closely as it goes to infinity. Denominator, the number or expression written below the line in the function. The main restrictions of a rational function can be determined by setting the denominator equal to 0 and solving. Any function of one variable x is called a rational function if and only if it can be written in the form f of x is equals to p of x over q of x, where p and q are polynomial functions of x and q of x is not equal to 0. Note that every polynomial function is a rational function with q of x is equals to 1. A function that cannot be written in the form of polynomial such as f of x is equals to sin of x is not a rational function. However, the adjective irrational is not generally used for functions. A constant function such as f of x is equals to pi is a rational function, since constants are polynomials. Note that function itself is rational, even though the value of f of x is irrational for all x. Domain of a rational function given f of x is equals to p of x over q of x. The domain of this rational function is a set of all values of x for which the denominator q of x is not 0. Domain restrictions can be calculated by finding singularities, which are the x values for which the denominator q of x is 0. The rational function is not defined for such x values, and these values are excluded from the domain set of the function. Factorizing the numerator and denominator of rational function helps to identify singularities of algebraic rational functions. Singularity occurs when the denominator of a rational function equals 0, whether or not the linear factor in the denominator cancels out when a linear factor in the numerator. Let's try this example. F of x is equals to x squared minus 3x minus 2 over x squared minus 4. The domain of the function includes all values of x, except where x squared minus 4 is equals to 0. We can factor the denominator to find the singularities of the function. X squared minus 4 is equals to x plus 2x minus 2. So the domain includes all x not equal to 2 or negative 2. Let's proceed to example number 2. Given f of x is equals to x plus 3 over x squared plus 2. The domain of this function is all values of x except those where x squared plus 2 is equals to 0. However, for x squared plus 2 equals to 0, x squared would need to equal negative 2, since this condition cannot be satisfied by a real number. The domain of the function is all real numbers. Asymptotes of irrational functions. A rational function has at most one horizontal or oblique asymptote, and possibly many vertical asymptotes. Vertical asymptotes only occur when the denominator is 0. In other words, vertical asymptotes occur as singularities, or points at which the rational function is not defined. Vertical asymptotes only occur at the singularities when the associated linear factor in the denominator remains after cancellation. Let's try this example. Given f of x is equals to 2x squared plus x plus 1 over x squared plus 16. Because the polynomials in the numerator and denominator have the same degree, which is 2, we can identify that there is one horizontal asymptote and no oblique asymptote. The coefficient of the highest power term is 2 in the numerator and 1 in the denominator. Hence, horizontal asymptote is given by y is equals 2 over 1 is equals to 2. Let's move on to the second example. Given f of x is equals to x minus 1, x plus 2 over x minus 1 squared, x plus 1. Notice that based on the linear factors in the denominator, singularities exist at x is equals to 1 and x is equals to negative 1. Also notice that one linear factor, x minus 1, cancels with the numerator. However, one linear factor, x minus 1, remains in the denominator because it is squared. Therefore, a vertical asymptote exists at x is equals to 1. The linear factor x plus 1 also does not cancel out. Thus, a vertical asymptote also exists at x is equals negative 1.
Good day everyone, I'm Katrina J. A. Tanio and I'm here to continue the discussion about rational functions. Finding the x-intercepts of rational functions. F of x equals x squared minus 3x plus 2 over x squared minus 2x minus 3. Set the numerator of this rational function equals to 0 and solve for x. 0 equals x squared minus 3x plus 2 equals x minus 1 times x minus 2. Solution for this polynomial are x equals 1 or x equals 2. This means that this function has x-intercepts at 1 and 2. Another example, f of x equals 1 over x. Here, the numerator is a constant and therefore cannot be set to 0. Thus, this function does not have any x-intercepts. In order to solve rational functions for their x-intercepts, set the polynomial in the numerator equals to 0 and solve for x by factoring where applicable. Rational functions can be graphed on the coordinate plane. We can use algebraic methods to calculate their x-intercepts, also known as zeros or roots, which are points where the graph intersects the x-axis. Rational functions can have 0, 1, or multiply x-intercepts. Simplifying a rational expression. Rational expression can be simplified by factoring the numerator and denominator where possible and canceling terms. X squared plus 5x plus 6 over 2x squared plus 5x plus 2. This expression must first be factored to provide the expression x plus 2 times x plus 3 over 2x plus 1 times x plus 2, which after canceling the common factor of x plus 2 from both the numerator and denominator gives the simplified expression x plus 3 over 2x plus 1. Multiplying rational expressions. Rational expressions can be multiplied and divided in a similar manner to fractions. Recall that when two fractions are multiplied together, their numerators are multiplied to yield the numerator of their product and their denominators are multiplied to yield the denominator of their product. X plus 1 over x minus 1 times x plus 2 over x plus 3. Multiplying these two expressions, we have the product x plus 1 times x plus 2 over x minus 1 times x plus 3. Multiplying out the numerator and denominator, this can be written as x squared plus 3x plus 2 over x squared plus 2x minus 3. Notice that this expression cannot be simplified further. Dividing rational expressions. Dividing rational expressions follow the same rules as dividing fractions. Recall the rule for dividing fractions. The dividend is multiplied by the reciprocal of the divisor. The same applies to dividing rational expressions. The first expression is multiplied by the reciprocal of the second. X plus 1 over x minus 1 divide x plus 2 over x plus 3. Rather than divide the expressions x plus 1 over x minus 1 and x plus 2 over x plus 3, we multiply x plus 1 over x minus 1 times x plus 3 over x plus 2. Then, multiplication is carried out in the same way as described. X plus 1 times x plus 3 over x minus 1 times x plus 2 equals x squared plus 3x plus 3 over x squared plus x minus 2. That's all for the rational functions reported by Gia Alaika Bangkale and Katrina Joy A. Tanio.